There's
She's sort of trying to explain anything, and when like she just randomly yells certain words.
Yeah.
I'm like, I don't even want to know what I was sorry.
For slide, you're also like, here's how this works, but doesn't explain how it works.
Yeah.
It's just like, this code works.
So, yeah, a C-based pointer is just like a reference variable in Java. So when we draw, if I'm drawing something out and I draw a box with an arrow that points to something, that is a pointer. Except in Java, it's not something that you can manipulate. When you set that pointer to point at something, you can only make it point at something else or at null. You don't have any ability to directly manipulate the pointer in memory. Because what that pointer is pointing to, it isn't pointing to an actual entity, it's pointing to a memory address. However, in Java, you don't know what that memory address is and can't manipulate. In a C-based language, you can. So if you want to be able to say, all right, this object, I now want to access the integer that represents the memory address that it's stored at. Then you use the ampersand and you go from the variable that you're looking at to, all right, now I want to look at where it's stored. So that ampersand is a shift from the actual entity to its position in memory. Whenever you use a star something, you are saying, all right, going from the memory address, I now need to access the element that is stored at that memory address. So they're kind of opposite in that regard. Ampersand to go from entity to memory address, star to go from memory address to entity. Whenever you pass something by reference, you're not actually passing the object, you're passing a pointer that says, I am a number that's telling you where that object is in memory. So if you wanted to do something like add 4 to that, or change up where you can use pointer arithmetic and actually end up at whatever is at a different memory address that's relative to this other memory address. And that's something that Java does not allow you to do because it just assumes that you don't know what you're doing. And C-based languages, all training wheels are off. This is something you can manipulate. By all means, please manipulate it. Just know what you're doing, because if you access memory that you don't have access to, you can do some pretty bad things. So make sure you know what you're doing. A bug in a C-based program can do a lot more than just crash your program. It can crash your computer. It can permanently. It can do some pretty bad things. There are usually some built-in don't do something absolutely terrible, like you don't have access to this memory. The OS actually protects you from it, but in general, it does that because efficiency and power. I can certainly talk about pointers more in office hours if people are curious, but we got to get through hashing and hash codes. Any questions before we start? This is going to be a you want your brain turned on day, because this is a little bit. Yeah. So we talked about the concept of representing a math set via an array list or a linked list, and we found that a lot of the operations would actually take quite a long time. So the motivation for learning a hashing structure is that we want to be able to represent a math set where these operations aren't quite as expensive as they are if we use an underlying list. So that motivates the use of a hash set or some kind of hash. So we just talked about what should we allow a set to be able to do. We know that sets can union, they can intersect, we can find a set difference. Everything else that we want to do with a set. Now let's talk about how we can actually do it. So this becomes a complexity-based argument for why we should introduce something new. But let's actually take a look at what a hash code is. Anyone familiar with the concept of a hash code? Couple people? That's probably most people in here. So a hash code is really just an integer-based representation of a more complex object. So we need the ability to convert anything, any primitive variable, any object that we would write, literally anything into a number. And that's all a hash function is. It's a conversion function of some complex object into an integer, yeah.
Is hash codes related to like hashing and password and stuff?
Yeah.
They turn into.
Yep. Yep, that's exactly what we're gonna study, is exactly how that is done. So any built-in Java object has a hash code that you can just use. Any object you can call .hash code and get back that integer. However, for anything that you write, you need to write that hash code function if you would like to be able to hash that object using any kind of built-in hash or anything else. So you'll need to define that for anything you write. So you will have to override that hash code. But anything that's built in has it for you, you can just call it. So if you're writing a hash code method, what do we want to be or even need to be true? What is the purpose of that hash code? What do we need to ensure as we write this so that the underlying goal is met? So the first one, every single object needs to have a unique hash code. Or sorry, it's better written here, one and only one possible hash code, not necessarily unique. We can't have two objects hashed to the same value, but a particular object has a particular integer that that function relates it to. So if I am a person object and I were to hash myself, there would be a single integer. And every time I ran this hash code function on me, it would generate that same integer. It's not going to generate a different integer if I do this tomorrow or next week or next year. It's always the same result. And then wherever possible, a hash code should map to a unique object. That means that that integer should represent the fewest number of possible objects. This is not always possible. It's usually not possible, so we need to design something that intelligently minimizes collisions where two different objects map to the same value. It's going to be impossible to do that all the time, but we want to minimize the frequency of it occurring. Does that make sense? The reason is there are going to be so many more possible objects than there are valid integers that we can map them to, usually. Of course, there are how many possible integers? 2 to the 32nd? 2 point something billion of them? That's quite a few. So as long as there aren't 2 point something billion possible objects in the construction of that object type, then you will be able to have a unique hash as long as we have some function that spreads the domain of all possible objects onto the domain of possible integers. But you can imagine there are some objects that have more possible values than that. How many possible doubles are there? How many possible strings are there? We get into, there are an infinite possible strings, right? There's strings aren't bounded in length, so there are an infinite number of possible strings. As long as our hash function is intelligent, that means we want some kind of even distribution wherever possible across all of the integers. So if we try to hash every single string of length 40 or less, if it's a word or not, doesn't matter. That would be significantly more of those than there are integers, but we want some kind of uniform distribution where it's equally likely that any particular one of those words or strings maps to a particular integer. So how do we do this in general? If it's a user-defined object, we're just going to go through every field of that object, and we're going to convert it into its associated integer via its hash code. So for an object, it has a bunch of fields. Each of those fields are either built in which case there's already a hash code function for it, Or it's user defined, in which case we would have already written a hash code function for it. So to define a hash code function for this object, we break it down into every field and every value that each field has. And then we construct some kind of expression that is going to take all of those numbers and map those to a single number. And that becomes the single number hash code representation of this object. There's a lot there. Any questions about any of these concepts?
Would you really draw it out for me or no?
There's not a ton I can draw here, except that if you can imagine kind of all numbers between the largest negative possible integer and the largest possible integer, the goal is to, for any particular object, we want to randomly, as the best of our ability, randomly pick a number that it maps to. Maybe I map to 1, you map to 2, the person next to you maps to 3, that person you would point out all the way across the room maps to 4. But the idea is no one maps to the same number, and now there's some numerical representation of you, as well as whatever it is that your object type is, whatever it is that your fields have, but there's some number that you are. However, with that function, it's possible that both you and that person you would point out across the room both map to the same number. Then if that number is called or used in some capacity, there's ambiguity between which object I'm referring to.
Pretty much like when you take a pen,
Yeah,
because there can be 2 cases.
yeah, yeah. So you want it to be a unique identifier wherever possible, but because we have a constraint on the target range of our possible integers, overlap will happen. We just want to minimize the chances. Other questions? I'll have the ability to draw out as soon as we get into exactly how this is done. So to do this, we need some kind of hash table, because we now need to store these objects. The goal is to be able to store these objects somehow in an easily searchable way. Remember that for the mathematical set, if we wanted to add something, we had to go through the entire set of objects looking for it, because there's no order and there's no multiplicity to it. So because there is no order, it's difficult to sort something. Even if you could sort it, the process of sorting takes a while. But then you'd still have to go through a binary search to go find it. If you wanted to remove, then you'd have to do the same thing. If there was any way that data could become out of order in the internal representation of the data, you'd have to resort it. If you ever removed items from it, then you still need to move everything back. If it's an array list or if it's a linked list, whenever you wanted to do something like get, there's no direct reference to that object, so you have to iterate to get to it, even if you knew which index it was at. So regardless, each of these are a linear time operation. But if you store something like a hash, the goal, if you use a hash table, the goal is to use this integer that is developed via this hash code function as a way of identifying if this object is in this structure, it's going to be right there. So to do that, we need a hash table, because the integer itself isn't going to tell us anything unless we make an array of size 2 to the 32nd to store every possible integer. We don't have that amount of space to be able to do that, so we need a hash table to be able to do this. So the goal is to make a faster add and remove. To do this, we need to know the position in the array that we are looking for. We can't be searching for it. We need to know if it is stored in this table, it is stored in a particular index. And that index will be based off of its hash code value. So how could we do it? You have some really large integer that represents you, and you need to store it in an array that is smaller than that. How could you do that? Let's say I make an array of size 1000. Because that's how much space I'm willing to dedicate to this problem. And your hash code happens to map to 719,274,906. How would you do it? Any thoughts? The answer is, we just mod it. Use modular arithmetic, and regardless of the size of that value, if my array was size 1000, then I just take the last 3 digits of the number. And say the last 3 digits of that number were 906. All right, I'm going to look in position 906 in the array. And that would be the unique storage location for that value. If it's in the array, it's going to be at that value. So basically you take the hash code value and you mod it by the underlying array size, and that tells you where you should look to go find it. Of course, there are issues with this. Can anyone identify what some of the issues would be?
Is there more than one that ended in 906?
Yeah, if you have multiple numbers that end in 906. What can we do about that? There are a couple things that I will talk about for ways to deal with that, but that certainly is a very important consideration, right? There could be 2 different objects that map to the same location that we're trying to store them in. As the target array that we're storing things in gets smaller and smaller, the likelihood of what we're going to call collisions increases. So what happens in the extremes? If we have an array of size 1, every element will map to it. This seems problematic. So having an array size of 1 doesn't do anything for us. On the other hand, we could have an infinitely large array. That's outside of the scope of feasibility, but if we had an infinitely large array, then every element would have a unique place in that infinitely large array where it would map to. And we could always identify it if we could just go to it. So this creates a kind of trade-off that we see all of the time in data structures and algorithms, which is that of space versus time. You can optimize for one, but improving one usually leads to worse performance in the other. So you can make your algorithm faster, but the detriment to making it faster is it's going to take more internal space to store more things so that you can reference them faster. If you make a ton of space, you can make your program really fast. If you're limited in the amount of space that you can allocate for a particular task, then the detriment to that is going to be it's going to take longer because you can't store as much. So in this case, if we don't have the space limitation, we just make a really large array, and then the chance of collisions are very small. Unfortunately, we don't have infinite memory that we can throw at every possible task. So there needs to be some limitation to the size of our hash table. If we don't have a time limitation, then why are we bothering to do this? We should just use this with a list, and O of n for every major operation is fine. Of course, for large projects, we need performance that's faster than that. It works if your underlying use case is very small, but as soon as this starts to scale, we need some kind of middle ground between these 2 extremes. So if you have both a space and time limitation, then hashing is the best thing you can do. So this is what we will actually do. We just need to think about the downsides to having limited space and limited time and account for those. All right, we're gonna take an aside here and talk about how do we compute a hash function? How do we actually, in practice, write a hash function? So ideally, what we want to be able to do is scramble these hash codes, creating a perfectly uniform distribution. We have a table, a hash table, that is our underlying array-based structure that is going to store all of the data. And the idea is that given all of our data, we have the same number of keys that map to each of those indices. As an example, let's take phone numbers. There are lots of possible phone numbers out there, but we only have space to store 1,000 phone numbers. Let's say we aren't going to have more than 1,000 phone numbers. Maybe this is a database for a local event that's going to have a few hundred participants. And we want to be able to easily access their phone numbers. So we would need some kind of hash function that takes a phone number and maps it to an integer between 0 and 999, the legal indices in a 1,000 index array. So, any thoughts about what that hash function could be? Take a phone number, make it as likely as possible to end up in anything between 000 and 999, but you need to come up with the formula that takes as input a phone number and spits as output some number between 000 and 999. Any thoughts on what some good or bad approaches to that would be? Maybe it's more fun to think about what are some bad ways to do this? What would create the most collision overlap? Yeah, it's probably not possible in practice that everyone has the same phone number.
I mean, we organize them by area code or something.
Yeah, that's actually exactly what I was thinking of. So if you took the first three numbers of someone's phone number, and this was a local event, then a lot of people would have the same area code, and you get really bad collisions around here with the 509 area code. Everyone would map to 509, and we'd just get collisions all the time.
Have it also have a lot of collisions just off of sheer coincidence.
Yes, but it's certainly more randomly generated. So if you do the last 3 digits, not even the last 4 digits, the last 3 digits, because we need to get something between 000 and 999, that would be a better distribution than using the first 3 digits. I'm not necessarily stating that that would be perfect, but you can use intuition to figure out, okay, if I need to come up with an intelligent hash code for this, there are some better choices and there are some worse choices. The goal is to the best of your ability, create that uniform even distribution where given a random phone number, it with equal likelihood would map to any of those positions. Of course, we need a different approach for each different key type, depending on its data type. So typically we offload this to a hash code method so that we don't have to think about it while we're writing our programs. If we need to make a hash table, unless we're inventing our own objects and using those to hash, we don't want to think about it. There is an existing hash code method we can just call. And if we do make our own objects, then we don't want to think about it every single time we do this. So we're going to write a hash code method once and then forget about it. And we can call it whenever we need to hash this type of object. So in general, how does this work for primitives? We'll start with primitives and move to every other type. So for integers, it's already done for us. An integer is already in between integer.min value and integer.max value. Great, just return it. And that is its hash code. Of course, there are some numbers that are more likely to occur in practice than others. It turns out that that's mostly okay because we don't know the size of the table that we are storing things in. Based on the size of that table, we're going to mod that number anyway. And that gets us to a fairly even distribution without worrying about it too much. For Booleans, you're going to select 2 primes. And if the value is true, you'll return one of those primes, and if the value is false, you'll return the other one. Doesn't really in practice matter which that they are. You will just find that with primes, it makes the math a little bit easier. And if we use primes, it actually avoids collisions more frequently. For doubles, we need to make sure they're in the IEEE 64-bit representation, which most programming languages store their doubles in anyway. So are we familiar with how doubles are stored internally? We basically break it down into 3 segments. There's the, well, it's really 2 segments. There's the number, so everything that would become before the power, the times 10 to the whatever, so we're going to store that. And then we're going to store the power. And basically that becomes a shifter in space. So we have a precision and then we have a magnitude. It's kind of the 2 ways to call it. The precision tells us what are the digits, and the magnitude says where do we manipulate the decimal to make it larger or smaller. So if we wanted to do this and convert that concept into an integer is only 32 bits. But we have a 64-bit representation of a double. So we need to map the 64 bits of that precision and magnitude onto some number. And the way that we're going to do it is we're going to split the number in half. There's going to be a first 32 bits and there's going to be a second 32 bits. We're going to overlay them on top of each other and we're going to XOR them. If you're not familiar with the XOR function, it's the exclusive OR. It's true if one or the other, but not both, are true. Yeah. We find that we use them a lot, especially in low-level programming, where you need to understand the underlying representation of your data. So you take this 64-bit number, you basically put the first 32 bits and the second 32 bits on top of each other, and then you're going to look at, all right, in the very rightmost position, is it a 0, 0 or a 1, 1? If so, the result is 0. Is it 0, 1 or 1, 0? If it is, the end result is 1. And you're going to go pairwise bit by bit through those 32 bits to get a 32-bit number or a 32-bit output. And that becomes your 32-bit integer that represents the hash code of that double. Does that make sense? Here's the code that would get it done. If you've never seen a bit shift in code, that is a Java-based bit shift. Basically, you're taking the first 32 bits and the last 32 bits, and the caret XORs them together. Question?
It's going from 64 to 32 bits. Half the unique number of hash codes that we store without collisions.
There certainly would be collisions, so there are more possible doubles than there are integers. Significantly so. Is that, I'm not sure if I 100% got the question.
No, I don't think I'm saying that right, so
If you can think of it, let me know. I'd be happy to. So yeah, we're basically saying we're going to take the entire number, we're going to bit shift it by 32. So you take the entire thing, move it over. So that gives us the 32 and 32 overlaid on top of each other. Then we XOR those 2 things and cast it as an int. And that gives you the hash code for a double. Actually doing this in practice is usually not necessary. I present these just because it's interesting to know how things are done underneath the hood. But if you call a hash code on a double, this is what will happen. And you don't have to ever write this logic, but this is how it is done. For strings, we use Porter's method. Porter's method says you're going to take some prime. Some 31 is particularly popular as a small prime. 17 can be used. It doesn't really matter what you use, just some small prime. And you're going to take the ASCII value of every character in the string and treat it as a particular exponential place. So you take the S of 0 is the first character in the string. You're going to multiply it by 31 to the power of the length of the string minus 1. Then you're going to add that to S of 1 times 31 to the L minus 2. And you continue that for every character in the string until you get down to the last character, which you multiply by 31 to the 0, which is just 1. And each one of those characters' values is the ASCII code value of that character. We're familiar with ASCII codes? Have we seen those before? Anyone need a refresher on ASCII codes as to what they are?
But no, never mind.
Yeah, it's the integer-based representation of characters. So if you've ever done something like cast a character as an integer, you find that capital A is 65, lowercase a is 97, etc. And all the capitals are adjacent to each other, as you would expect. All the digits are adjacent to each other. All the lower cases are adjacent to each other. So each character has some numerical representation that we call an ASCII code. I do not have this in summation notation, unfortunately. It would be, yeah. So from I equals 0 to L, you would want to take S of I times 31 to the L minus I. Or L minus I plus 1, there we go. So implementation of this, you just basically do this iteratively, because anytime you have a summation, as we just pointed out, we can just write a loop for it. So breaking down the summation into a loop, you just basically go character by character and add to the existing character, the existing total that you are calculating. And eventually you're going to have some large integer, and you return that. Now, do we imagine that this possibly overflows the size of an integer? We're doing some pretty large scale exponential arithmetic, so it's very likely that this overflows an integer. What's nice about that is it just wraps around. And because we're only interested in an output between integer.min value and integer.max value, that wrapping around is just fine. We don't care if this turns into a negative number, or if this just wraps around a bunch of times and becomes a large number, but not the correct large number. That's okay. We just store this as an integer, and whatever it ends up being is great. The goal is just that we get that uniform distribution as much as possible over all possible integers. And this does a very good job of that. So S of I is the ASCII value of that character in the string, and you get this. Again, strings have an underlying hash code written in Java. You don't need to write your own for strings, but I thought I would at least show you how it is done in case you were curious. You have your own types. So how do you write a hash code for your own user design types? This one is very important because it's the one that isn't implemented when you go to make your own custom objects. So we're going to use a very similar to Horner's rule, 31x plus y rule. And again, the 31 can be any small prime. 31 is particularly popular. How will you do it? You initialize your hash code to a small prime. For every field, you're going to multiply the existing hash by this, whatever we've attached to X, this 31, and then add that field's hash code value to that. So even though that might be a string that has a large scale exponential to figure out what that value is, you'll take the existing hash code, multiply it by whatever that string field's hash code ends up being, and then, 31 of the existing times the existing hash code plus the new hash code. And that gives you a new iterative hash code. And once you do this for every field in the object, then you return the final hash code. So let's say we have something like a person object that has an int age a double salary and a string name. Why not? Those are the three things that are important to a person object. So you take the int, we start with 17 as our base value. We're going to compute the value of the hash code for the integer, which is return itself. We would take the 17 that is our existing hash value, multiply it by 31, and then add the value of that hash integer to get a new value. Looping around, we go to the next field. This one's the salary. We're going to IEEE XOR all the bits, get some 32-bit integer representation of that double. We take the old hash value that incorporated the integer, we multiply it by 31, and we add the hash code value of this double. That gives us a new value. We store that. We move on to the string. We use Horner's method to compute a hash code value for that string. We're going to take the existing hash value that accounts for the integer and the double. We're going to multiply it by 31, and we're going to add the result that Horner's method gave us for the hash code value of that string. And that gives us a new value. That's the value that we return for the hash code for this object that incorporates every field in that object. Does that make sense? If we do this the same way for all objects, note that we get that guarantee that if we instantiated two of exactly the same person object, they were exact, perfect copies of each other, but they had a different memory address. They would hash to the same value, which is good. If we have identical objects, we want to be able to find those objects at the same location. A different object is very unlikely to map to exactly that same integer value. If you had a different, if it was the exact same for two of those, the exact same integer, the exact same double, but the string was different. So same age, same salary, exactly the same salary, but differs in name. It is very unlikely that they would be at the same location in memory. Even though they're very similar looking objects, they could be in vastly different places in memory because of this work that's being done. If you have a reference type, so something that refers to another object, you don't actually have that object stored, then you would need to recursively call its hash code. So as part of calculating this hash code, you would call that object's hash code to figure out what its hash value is. So you have some other user-defined type. A person has a pet object, and that pet object is user-defined. We would have to call the pet object's hash code to be able to get a hash code for that pet, because it's not built in and defined. For arrays, because arrays could be a type, you of course have to apply this to every element in the array. So if you have an array of 1,000 elements, you're going to call the hash code on every element. If it is a built-in array, so it's not an array list or a linked list, you can use arrays.deep hash code that will calculate it for you. So you get something that looks like this. This is the final code-based representation of a user-defined type. So we have three fields, a string, which has a built-in hash code because it's a Java-defined type, a date, which is also a Java-defined type. But you can imagine you wrote your own date class for it, and a double. Our hash code starts at 17, is updated to be 31 times that 17 plus the string's hash code. Then we update it again, 31 times the old hash code plus the hash code for the date object. And a double has a built-in hash as well. If you use the double class, that'll do it for you. Then you finally return that hash value. So that gives you an integer. So a hash code is really just an integer between -2 to the 31st and 2 to the 31st minus 1. As we would expect, those are the legal bounds of an integer. A hash function is just some index into a table, I like to think of them as arrays, between 0 and m minus 1. M is the array's size. So we use modular arithmetic to convert this hash code into an index. How do we do that? Just mod it by m. Is there an issue with just modding it by m? Can anyone see the issue with just doing this without any further corrections? Yeah,
Maybe confirm that M isn't 0. Something along those lines.
Yeah. yeah, that's close. It's very close. The biggest issue is if we do this, we allow negative indices, which is bad if we're trying to map to an array. So how do we deal with potential negative indices? Any thoughts?
They're absolute values.
Take the absolute value? That's a really good idea. So what if we took the absolute value? There's still an issue with this. Can anyone identify the very, very small issue with doing this? This will almost always work, but there's going to be a fun error that you find every so often. It's not frequent at all, but can anyone identify what that error would be? Yeah. So luckily, there's no real division happening anywhere here. We're modding, I guess, yeah, if you mod by something, you end up dividing it, but there's nothing that would say that we're dividing it by the table size and returning. So unless the table size were 0, we wouldn't be dividing by 0, but that's a great idea. Can anyone find the 1 in about 2.3 billion side case? What happens? Yeah,
Absolute value of -2 to the 31st.
yes. What happens if you take the absolute value of -2 to the 31st? You get 2 to the 31st, which is out of bounds. So we cannot hash anything with exactly the value -2 to the 31st. And to give you a sense of just how unlikely this is, it took people a long time to come up with an English sounding word that maps to exactly -2 to the 31st, but polygenolubricants maps exactly to -2 to the 31st. And if you use exactly that, then you will have a fun bug that is an array index out of bounds exception, or a hash code violation that an integer you can't have an integer that represents that value every few billion hashes on average. So how do we deal with that? That is a very fun password. If you ever just want to borrow that for fun, if someone tries to hash that and hasn't built in a good.
I want to actually be numbers.
And now I can hack all of your accounts. The real reason I do this, I'm kidding. So the best answer is just to take that value if we would hash something directly to -2 to the 31st and just say, you know what? It's okay if that hashes to 0. And twice as many elements will be contained at index 0 as anywhere else, but because there are so many of these, it ends up not really mattering that twice as many of them happen to map to 0. So you take that's the bitwise and with a single ampersand. Double ampersand is the actual logical and a single and is a bitwise and in Java. So you basically and it with the largest possible positive number and then mod it by m. And that means that anything that would have mapped to -2 to the 31st maps to 0 instead. So it takes what would have been an error and just sets it to 0. Questions on any of this? Yes. These exact slides? Could probably do that. So we're going to run with the assumption that we can hash equally, and we get a basically uniform distribution between 0 and this table size -1 for this table, however big this table that we want to produce happens to be. You can start to think of every array index as a bin, and you're just tossing balls into these bins randomly. So to hash, we just start throwing balls into random bins, and we end up with something that looks maybe like this. This would be something that you would expect if you wanted to throw 11 balls into 15 bins. It would look something like this if you did it on average. If we use this hashing function, there is no better way to guarantee an even distribution of objects. This is the best mathematical way we can use to ensure that over a large sample, we get as close to a uniform distribution as we possibly can. Of course, if our data is structured in some way that it has shape to it, meaning that it's more likely we're storing phone numbers and we know that they're all going to start with 509. If there's some pattern to the underlying data, sometimes there's something intelligent we can do with hash codes to better ensure a uniform distribution. Something like ignore the first 3 digits, if that ended up mattering, or something like that. So there's something that we could do if the data has patterns to it. But if it's randomized data, there's nothing better we can do. Over a larger sample size, it actually does very well. So if we use a table size of 97, and we'll talk about why prime table sizes are better than non-prime table sizes, then when we hash Tale of Two Cities, all of the strings, all of the words that appear in Tale of Two Cities, even though certain English words are more likely than other English words, we still get a pretty darn good distribution when you mod them by 97. That looks pretty uniformly distributed. And in practice, this is what we are going for. Not something that is perfect, but something that is reasonably uniform. All right, now we've got to talk about the elephant in the room. What happens when 2 elements map to the same location? The downside to using an array that's not just every possible integer in size is we actually have collisions. If you use a table size of 97, as soon as you insert 98 things into that, you're guaranteed to have at least 1 collision. So, of course, some objects we want to store could have the same index. What could we do? We could, of course, use more memory, but if we could have, we would have. Imagine that we're already at the maximum allowable size of memory that we want to dedicate to this problem. So when we have a collision, we need to handle it. And we want to be able to handle it efficiently. Any ideas of what we could do? 2 objects map to the same location. We can only store one of them at that location. What could we do to be able to store the second element that also maps to that location? Yeah?
Is it possible to just run the same object through a hashing function again?
It would return the exact same value. If it's the same object, it will always give you the same hash value, which that's a good idea. But then if it could generate a different one, and then I said, go fetch this, how would you know where to go look? If the hash function generated something different, then what if I look here? What if I look here? What if I look here? You might as well do a linear search at that point. So we want to be able to find that item again efficiently once we store it. So it's a good idea. Anything else? Yeah.
Have the object have a field that points to the other object.
Okay, so that is actually one of the real solutions, is that each one of these indices in an array is the head of a linked list. And then you start storing everything that maps to that same hash in a linked list at that element. So if we look at the past visual here, each one of these indices would be the head of a linked list, and every word that maps to that would be another node in that linked list. That's usually the best solution. There's a little bit of a concern of if these lists get really long, it has all of the downsides of a linked list. It's just that we've cut the size of the entire storing everything by a factor of 97, because we have heads of 97 linked lists, and we know which sublist to go look in to go find the thing. But we'll talk about other ways that we can solve this and the benefits and detriments of solving it in each one of those ways tomorrow.
Are we going to be writing them up for a while?
We are not, it's actually the next paper assignment where I will be having people hash small things kind of on paper.
Is that?
Yeah, so wait for code for a bit before we come back and have a big coding exercise for the next assignment after this. But
That'll be good. I just thought they were like.
yeah,
I can see.
yeah. It's really important. A lot of security has to do with, you need to store a lot of stuff. If you want to attack it, you didn't know about it before, so that you can. Use non-determinism, it's really efficient.
Yes, like you guys. Like I'm not enough to store.
Use this theoretical concept that doesn't exist. Oh, yeah, non-determinism basically, like, if you do it the fastest it is, how long does it take? So you can just type in the associated password. Great for fast, you just know it already.